Most people have no idea what's actually happening inside their body when they go for a walk. They think it's about steps, maybe calories, maybe getting some air. But there's a hormonal shift that starts occurring inside your muscles around the 20 to 30-minute mark, one that doesn't happen during a short walk. And it quietly determines whether your body burns stored fat or keeps locking it away. It comes down to one hormone, insulin. And once you understand what walking does to it, you'll never look at a 10-minute stroll the same way again. The hormone running the show every time you eat a sandwich, a bowl of rice, even a piece of fruit, your blood sugar rises. Carbohydrates break down into glucose and flood into your bloodstream. Your body can't leave that glucose floating around unchecked, so your pancreas releases insulin to handle it. Insulin's job is essentially to unlock your cells so glucose can get inside and be used as fuel. But insulin isn't just a delivery driver, it's also a storage signal. When insulin is elevated, your body interprets that as energy is plentiful, hold on to everything you have. Fat cells stop releasing stored fuel. Your body shifts into conservation mode. Fat-burning enzymes get suppressed. For millions of Americans right now, insulin stays elevated not just after meals, but throughout the day. Not because they're eating constantly, but because modern life has removed the one thing that historically kept insulin in check: consistent movement. Sit at a desk for 8 hours. Drive home. Sit on the couch. Your muscles go quiet. And when your muscles go quiet, they stop clearing glucose from your bloodstream on their own. So your pancreas keeps pumping out insulin to compensate. Over months and years, cells stop responding to insulin as effectively. The pancreas has to release more and more just to do the same job. This is insulin resistance, and according to data from the CDC as of 2025, roughly 98 million American adults have prediabetes, most of them without knowing it. Walking, specifically walking long enough, is one of the most direct ways to interrupt this cycle. What happens in the first 10 minutes? The moment you stand up and start walking, your muscles immediately start contracting. Each step requires energy, and your body starts pulling from the most available source, glucose already circulating in your bloodstream. Blood sugar begins to drop slightly. Your pancreas senses less glucose and dials back insulin output a little. This is real, it's measurable. A short walk after a meal does smooth out blood sugar spikes somewhat, and that's genuinely useful. But here's what most people miss. At 10 minutes, your body is still in reactive mode. Insulin is still the primary manager of glucose. The pancreas is still doing most of the heavy lifting. Your muscles are consuming what's available, but they haven't yet switched on the deeper cellular machinery that truly changes your metabolic environment. Think of it like starting a car engine but not actually going anywhere. The engine is running, things are warming up, but the real work hasn't begun. The deeper shift that starts around 20 minutes inside every muscle cell. There's a molecule called ATP, your body's main energy currency. Every muscle contraction burns through it. As you keep walking past that 10-minute mark, ATP gets used up faster than it can be replaced, and the cell's energy balance begins to shift. That shift activates an enzyme called AMPK, AMP-activated protein kinase. Scientists often call it the metabolic master switch, and that's not an exaggeration. AMPK monitors energy demand inside the cell. When it detects that demand is rising and energy stores are dropping, it sets off a cascade of responses. It ramps up energy production, improves fat oxidation, and most importantly, it starts moving glucose transporters to the surface of muscle cells. These transporters are called GUT4. When you're resting, most of them sit idle inside the cell. But when AMPK kicks in during sustained activity, GUT4 transporters migrate to the outer membrane like doors opening up. Suddenly, glucose can enter the muscle cell much more freely. Here's the key. This process doesn't rely heavily on insulin. Your muscles are essentially pulling glucose directly from your bloodstream using their own internal system. The more GUT4 transporters at the surface, the more glucose enters the muscle, and the less insulin is needed to maintain blood sugar control. Research published in journals like Diabetes Care and Medicine and Science in Sports and Exercise has consistently shown that this insulin-independent glucose uptake becomes meaningfully significant after around 20 to 30 minutes of moderate aerobic activity. The effect at 10 minutes is present but modest. At 30 minutes, it's substantially stronger. Why 30 minutes is the real threshold? By the time you hit 30 minutes of steady walking, several systems are operating together in a way they simply weren't at the 10-minute mark. GLUT4 transporters are highly active at the muscle cell surface. Glucose is being cleared from your bloodstream efficiently. Your pancreas detects lower blood sugar demand and reduces insulin secretion. And because insulin is lower, another process quietly unlocks. Fat cells start releasing stored fatty acids into the bloodstream. Normally, an enzyme called hormone-sensitive lipase breaks down stored fat so it can be used for energy. Elevated insulin suppresses this enzyme, but as insulin drops during a sustained walk, that suppression lifts. Fat becomes available as fuel again, not just glucose. Your muscles, now running low on easy glucose, start burning more of those fatty acids. The body shifts from running almost entirely on blood sugar to using a blend of glucose and fat. This is metabolic flexibility, and it's one of the most important markers of a healthy metabolism. Beyond the walk itself, the effects linger. Studies have demonstrated that a single 30-minute moderate walk can improve insulin sensitivity for up to 24 hours afterward. ULIT4 transporters remain more responsive. Blood sugar is handled more efficiently at your next meal even without exercise. A 10-minute walk does not reliably produce this extended effect. The cellular machinery simply doesn't get activated deeply enough. What this looks like in real life. Here's a practical way to think about this. Imagine two people with nearly identical diets and schedules. One walks for 10 minutes most days and calls it done. The other pushes to 30 minutes consistently. At the end of one day, the difference is negligible. At the end of 3 months, the second person's insulin sensitivity has measurably improved. Their blood sugar spikes less after meals. Their body accesses stored fat more readily between meals. Their energy levels are more stable because they're no longer riding the blood sugar roller coaster. Cravings calm down because chronically high insulin, which signals the brain to seek more glucose, is no longer running the show. The first person? They're getting some benefit, but the deeper metabolic recalibration hasn't happened. Their cells haven't gotten the consistent signal they need to adapt. This isn't about willpower or discipline. It's about biology and the minimum effective dose of a signal to change behavior at the cellular level. The adaptation that happens over weeks. When you make 30-minute walks a consistent habit, the body starts investing in the infrastructure needed to support that activity. Muscle cells build more mitochondria, the structures that produce energy. This process, called mitochondrial biogenesis, increases your capacity to burn both glucose and fat. More mitochondria means each cell can handle greater energy demand more efficiently. At the same time, the number of ULIT4 transporters in your muscle cells gradually increases. Your muscles become inherently better at glucose uptake over time, independent of any single walk. This is one reason people who exercise regularly have significantly lower rates of type 2 diabetes. Their muscles are chronically more equipped to handle blood sugar. After several weeks of consistent 30-minute daily walks, many people report something they didn't expect. Food tastes like enough. The afternoon energy crashes fade. Hunger becomes predictable rather than desperate. That's not coincidence. That's insulin behaving the way it was designed to. The bottom line, walking is one of the most underrated metabolic tools available to anyone, regardless of age, fitness level, or health status. But the biology is clear about one thing. There's a meaningful difference between 10 minutes and 30 minutes. Not because 10 minutes does nothing, it does something, but because the cellular systems that actually improve insulin sensitivity, activate fat burning, and create lasting metabolic change require enough sustained activity to get fully switched on. AMPK needs time to build, ULIT4 transporters need sustained contraction signals to mobilize, insulin needs enough glucose clearance to meaningfully drop. All of that converges somewhere in that 20 to 30 minute window. So the next time you're tempted to cut a walk short at 10 minutes, remember what's happening beneath the surface. Your muscles are just getting started. The deeper conversation between your cells and your metabolism hasn't begun yet. Push through to 30 minutes. Send your biology the right signal. That's when the real shift happens. If you found this useful, like and subscribe for more evidence-based content on metabolism, blood sugar, and the science behind everyday habits.